All right, so we're in section 7.6. We're going to talk about moments, center of mass. I'm just going to abbreviate COM. Center of mass and centroids. So just quickly, talk about terms a little bit. Mass is the idea of mass. It's a property of an object that resists motion. So what we're doing with moments and center of mass is we're dealing with a mass, and we're talking about its distance from an axis or from a point. So we're going to talk about moments about a point, and moments about a line. Moment just means we're taking some object and we're giving it some kind of weight based on how far it is from an axis. So when we're talking about center of mass, when we're talking about moment of mass, we have a mass, we have an axis, and we're giving weight to that mass based on, and by weight I mean we're counting it more based on how far it is from the axis. So we're going to, for what we're doing today, we're going to assume that we can take mass as concentrated at a single point. So we're not saying it's spread out, we're concentrating it at a single point. So if we talk about a moment, and we'll end up talking about quite a few moments over the course of the year. So the moment of a mass about a point is just the mass times the distance from the point. I'm going to say m times x if we're on the x-axis, distance from the origin. And we call x the length of the moment arm. So if we draw a quick sketch, here's our x-axis, here's our mass sitting out here. This distance is x. So the moment is just the mass times x, and we call x the moment arm. So that would be the moment of the mass about the origin. So for a one-dimensional system, if we have a bunch of masses distributed along our number line, the moment about the origin is just the sum of the individual moments. So we just add up our moments. M sub 0 about the origin is m1 x1 plus m2 x2 plus dot 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 plus however many we have, m sub n x sub n. And these are masses that are located at these particular points. So this is we're kind of looking at this as like a balance beam, and we're placing masses on either side of the origin, and the moment talks about how the masses are distributed. The center of mass of this system, and we use x bar for the center of mass, is our moment over the total mass. So the center of mass of a one-dimensional system is just like I said, like a balance beam. It would tell you where you would have to place a point, and that system would balance at that point. That would be the center of mass. So we would find the moment, divide by the total mass, and that would give us the x-coordinate of the center of mass, about the origin for a one-dimensional system. So we just multiply the mass times the distance from our object. So idea of moment about the origin, pretty straightforward. We're just basically, like I said, we're talking about kind of a balance beam. Where does that where will it balance if these masses are distributed this way? There are lots of different kinds of moments. We have a moment of mass. That's what we're talking about here. And again, moment just means we're taking this mass and we're giving it some kind of weight based on its distance from the axis. We could have a moment of force, which is what is called the center of gravity. Now, in a uniform gravitational field, the moment of force and the moment of mass is the same. We call the second moment of mass, where we multiply by the square of the distance from an origin, from a point, or from an axis. The second moment of mass is the moment of inertia, and we'll talk more about that in second semester. We can have moments of area. We can have moments of whatever quantity we want it. We take that quantity and multiply it by distance from the axis. In statistics, there's a third moment that has to do with the distribution of data. We talk about a third moment for something. I'm not 100% certain what that is because I'm not a statistics person. For a two-dimensional system, we can define two moments. One with respect to the x-axis and one with respect to the y-axis. So for a two-dimensional system, we talk about the moments about the coordinate axes. So one-dimensional system, nice and easy. Multiply the mass times its distance from the origin. That gives us our moment. Divide by the total mass. That gives us our center of mass. For a two-dimensional system, things get a little more interesting. And when we're talking here, where I'm talking about a system, I'm talking about individual, discrete masses concentrated at points situated along a line or in two dimensions. So when I'm talking about a system, I'm talking about discrete points of mass. Two-dimensional systems, we have two moments. We have a moment about the x-axis and a moment about the y-axis. So if we have a two-dimensional system and we have masses, discrete masses m1, m2, dot, 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 m sub n, and they're situated at these points. x1, y1, x2, y2, so we know the coordinates of all these masses. On and on to x sub n, y sub n. The moment about the y-axis. So this is where we need to pay a little more attention. So for a mass situated at a point, we and I'm going to write this m sub y. What's the distance of a point from the y-axis? If we have some points situated. Our mass is located at these points. What's the distance in terms of its coordinates of this point from the y-axis? X. That's where we have to be careful. M sub y is m1 x1 plus m2 x2 plus dot 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 m sub n x sub n. So the distance from the y-axis is given by the x coordinate. And the moment about the x-axis, we say m sub x. The distance of a discrete point from the x-axis is the y-coordinate. So we get m1 y1 plus m2 y2 plus dot 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 m sub n y sub n. This should be x. What about the x? No, about the y. This should be x. So the moment about the y is given by multiplying the masses times their distance from the y-axis, which is given by the x-coordinate. Moment about the x-axis, masses times their distance from the x-axis, which is given by the y-coordinate. And the center of mass. Of the system, we say x bar or y bar is x bar is given by m sub y over the total mass, and y bar is given by m sub x over the total mass. So that would be the center of mass of the entire system. And again, m is the total mass. So if we have a two-dimensional system, we just take our points of mass, multiply them by their respective coordinates if we're looking for the x center of mass and y center of mass, and then we divide each of those by the total mass to give us our center of mass. And the center of mass, we could think of that as kind of where that would balance. If we thought of this as a plane and the masses are distributed on this plane, that would be the point where that plane would balance with all those masses distributed out that way. So for discrete systems of masses, all we're doing is adding up all these little moments to find the total moment of our system. So any questions so far about what we're talking about in terms of moments and in centers of mass? Where things get interesting is where we move from a discrete system to a continuous system. So because we're adding all of these up, what do you think is going to be involved? Integrals. Very nice integrals. So for discrete systems, we just add each individual one up, find the sum, we have our moment, and we can find our center of mass. What we're really interested in, just kind of a lead in to what we really want to talk about, is planar lamina. So what we're talking about here is a lamina is just a very, very thin sheet. We're talking about a thin sheet on a plane. So we're talking about a slice of something. So we're in the plane, so we're talking about a two-dimensional system. Lamina just means we're talking about a very, 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 very thin slice. We're assuming that we have so it's like a flat plate of material, and it has a constant density for what we're doing today. And our density here, because we're talking about a flat plate on a plane, we're talking about density per unit area. And we will deal with a variable density lamina second semester. We'll talk about double integrals. We talk about a variable density planar lamina. And for these problems, we use rho for our density. And that's density is mass per unit area for a planar lamina. So what we want to do for a planar lamina, what we're normally going to have is we have our planar lamina is usually going to be some area between two curves. So there are curves, and we'll call this one F, and the other one, the lower one, G. And we want to find the center of mass of this area between x equals A and x equals B. So the problems you're going to be given will tell you, okay, find the center of mass of the region bounded by such and such and such and such, and then that's your problem. So what we're going to do is I'm going to sketch my region in the XY plane. So make a little sketch, doesn't have to be beautiful, doesn't have to be perfect. And we're going to then divide our region into strips. And our strips need to be parallel to one of the coordinate axes. Because I have my functions drawn above and below, I'm going to divide this into vertical strips. So there are my strips. And we're going to find the mass and center of mass of the strip. And then we're going to integrate over the region to find the center of mass of the region. So we're using the same idea that we've been talking about. We've talked about several times, where we're dividing our region into small pieces and then integrating to add all those pieces up. And so we need to find. We're going to find the moment about the x-axis, moment about the y-axis. We're going to find the total mass, and then we know that finally the x center of mass, x coordinate is m sub y over the total mass, and the y is m sub x over the total mass. Just like for a discrete system, but we're going to, rather than just adding pieces, we're going to integrate. So let's label a couple of other coordinates so we can develop these integrals. So the coordinates here is x sub I, and the y coordinates go over here, and this is the center of this little strip, and I'm going to call the thickness of the strip delta x. So the coordinate of the center of the little strip is x sub I, y sub I. So the mass is easy. Mass for a planar lamina is just going to be density times the area. Well, how do we find the area of this strip? So I'm going to write the density. How do we find the area between two curves? Integrate. So I'm going to do the integral. Let's write the integral from, we're looking at the region from A to B. How do we find the area of that region? Let's set up this integral. X goes from what to what? A to B. What's my integrand? What am I integrating? F of x minus g of x, right? dx. There's my total mass. The density, whatever my constant density is, usually the problem's nice and they say your density is 1. So the mass is just given by the area. The mass is proportional to the area. So the total mass is just f of x minus g of x. So this is just rho times the area of the region. So that's an easy integral. We know how to do that one already. The other one's not too hard. So we're going to find the moment about the x-axis and the moment about the y-axis, we're going to assume that the mass, we can look at the mass of this little rectangular strip as concentrated at the center. So because the density is uniform, we're saying the mass, we can write our integral as if the mass of that rectangle is concentrated at the center. So, if we're concentrating the mass of this rectangle at the center of the rectangle, we want to find the, let's do the easy one first. We want to find the moment about the y-axis. The moment about the y is the mass of this rectangle. Well, we already found the mass of that little rectangle. The mass is the area of the little rectangle, f of x minus g of x times dx times delta x. So the mass is f of x minus g of x. And we have this dx out here. We have something else to put in there. How far is it from the y-axis? Based on our drawing. X. The area is dx. It's dx units thick. So f of x minus g of x dx is the area of the little rectangle. X is its distance from the y-axis, or from the y-axis, right? So we're just going to integrate from A to B. Put the density out here because we need we're taking into account the mass. So the density times the area is the mass of the little rectangle. X is its distance from the y-axis, and that's our integral for the moment about the y-axis. Rho times the integral from A to B of x, f of x minus g of x dx. F of x minus g of x dx is just the area of that little rectangle. All right, the next one's a little trickier, but not much. The moment about the x-axis. I need rho. I need an integral. We know we're going from A to B. We know that we have the area of the rectangle. So f of x minus g of x dx is still in there. But we have another quantity now. Let's look at our drawing. How far is the center of this rectangle from the y-axis? Or I'm sorry, from the x-axis. Y, what's the y, how do we find the y-coordinate of the center of that rectangle? We know the y-coordinate of the top of the rectangle, that's f of x. We know the y-coordinate of the bottom of the rectangle, that's g of x. How do we find the point that's in the center? How do we find if we have x1, y1, x2, y2, how do we find the midpoint of that segment? That's a slope. How do we find the midpoint? x1 plus x2 divided by 2. And for the y coordinate? y1 plus y2 divided by 2. We're taking the average of the y coordinates, right? That gives us our midpoint. We know the y coordinate up here is f of x. We know the y coordinate down here is g of x. So the middle is the average. F of x plus g of x divided by 2. And I need to put a set of parentheses here. So f of x plus g of x divided by 2 is the y coordinate of the middle of that rectangle. It's the average of the top and the bottom of the rectangle. So my moment about the x is going to be given by this integral. This f of x minus g of x dx times rho is the mass of the little rectangle. This gives me the y coordinate of the center. And then we know that x bar is m sub y over the total mass, and y bar is m sub x over the total mass. And the mass is just given by the density times the area. So this integral f of x minus g of x dx shows up in all of these. That's the area of the little rectangle. We made the little representative rectangle. X is the distance from the y-axis. This f of x plus g of x divided by 2 is the distance of the center of that rectangle from the x-axis. And when we find our x bar and y bar, you see that rho shows up in each of these. So that cancels at the end. So the density doesn't even play a part in this. All right, we have any questions on our development of the center of mass? And what the center of mass would tell us is if we put a pencil at the center of mass of that planar lamina, that planar lamina would balance on the tip of our pencil. Balance pencil flat. So in general, when we have a planar lamina center of mass problem, we want to sketch the region, divide it into strips. The direction that you divide it depends on your functions. I prefer to divide it vertically because we usually have our functions y equals f of x. Draw the little representative rectangle. You can even draw the little dot that's at the center to remind you that you're looking at the center of that little rectangle. And then we integrate over our region using these integrals to find x bar, y bar, and the mass. All right, let's look at an example of calculating a center of mass. Moments and center of mass of a planar lamina. So this is how your problems are usually going to be stated. We want the center of mass region bounded by f of x 4 minus x squared, and g of x is x plus 2. And we're going to say that rho equals 1, just to make our lives easy. All right, so we need to sketch this region and find our limits of integration. So 4 minus x squared, what's my graph look like? What is it? Parabola. Opens down So my parabola looks something like this. X plus 2 is a line. So we have a line that looks something like this. We need to find where they intersect. To find our limits of integration, how do we find where they intersect? Set them equal to each other. 4 minus x squared equals x plus 2. We end up with x squared plus x minus 2 equals 0. And that factors, we find that they intersect at negative 2, 0, and 1, 3. So we can set our representative rectangles vertically or horizontally, as long as we kept our graphs, our functions set up properly. I'm going to set my rectangle vertically like so. And that way the parabola is always the upper function, the line is always the lower function. If I set my rectangles horizontally, when I got to here, I would have to switch and do a different integral because the sideways rectangles would go from one side of the parabola to the other side. So this one not difficult. Now we're just back to calculating basically the area between the curves, plus a little extra stuff in our integrals for our x bar and our y bar. So our mass, which is given by our area, is just the integral from negative 2 to 1 of 4 minus x squared minus x minus 2 x plus 2, thank you, dx. Not a difficult integral to evaluate, and we're going to say rho equals 1, so I'm not even going to put it into the calculation. So this comes out to, when I evaluate this, I get 9/2. Not a difficult one to evaluate. M sub y, the moment about the y-axis. So the y-axis, our distance of the center to the y-axis, is just given by x. So I have the integral from minus 1 to 1 of x times this quantity. When I subtract this out, I get 2 minus x squared minus x. Should be minus 2. So this is my moment about the y-axis. And again, we end up with polynomials, not a difficult integral to evaluate. And this comes out to negative 9/4 when I evaluate that. And then m sub x, a little more difficult to set up, but not difficult to do. So I have 1/2 f of x plus g of x. When I add those two together, I get 6 minus x squared plus x. That's the f of x plus g of x divided by 2 times the area, 2 minus x squared minus x dx. Multiply this all out, evaluate the integral, and this comes out to be 54/5. We just end up with polynomials here, so this is not a difficult one to evaluate. And x bar is m sub y over m, which comes out to negative 1/2. And y bar is m sub x over the mass, which is 54/5 times 2/9, and I get 12/5. So my coordinates of my center of mass would be -1/2, 12/5. And it's always a good idea when you calculate these to make sure that makes sense. So I look at this region. Would the place where it balances, would the x-coordinate be negative? Well, it looks to me like most of the mass is over here. So the x-coordinate of my center of mass would probably be negative. And the coordinate of the center of mass would have to be up here somewhere. This is 3, so somewhere between 2 and 3-ish. So we can look back and see if our answer makes sense in terms of what our coordinates come out to be. So not difficult to set up. Sometimes the integrals, depending on your regions, the integrals can be a little tricky to evaluate. But we're just following our template for setting up our for our integrals, assuming that mass is concentrated at the center of those little rectangles. Tomorrow in class, I will talk about an extension of this. And let me see, would it be helpful again, because we ran out of time, would it be helpful again for me to post another center of mass calculation example online? Yes? Okay. I will do another example of finding a center of mass of a planar lamina, and I'll post that to my website. All right, homework. There you go.